Okay, now let's look at the probability distributions associated with the states in a Markov chain and see how that is different from the one-step transition probability metrics that we extracted in previous slides. So remember, I defined the vector Q at some point in previous videos, and vector Q shows the distribution of the state of the system at the start of the analysis. So for example, if I develop the vector Q for the example in which we had the sunny and cloudy day, if Q is, for example, 0.6 and then 0.4. Okay, and remember we had two states, sunny and cloudy days. So what does this vector Q mean? That means right now we may not know exactly if our weather is sunny or cloudy, but we know it has 60% chance to be sunny and 40% chance to be cloudy. Okay, so that's the probability of, that's the distribution of the state of the system right now, okay, at time 0. And most of the times the situation that we are dealing with is that we may not know exactly what is the state of the system right now. We just know the distribution of the state of the system, meaning that we know the probability that the state of the system is in any one of the possible values, and we want to know where are we going to be, for example, after n possible transitions. Okay, so where can we be after n possible transition would be probability distribution of the state of the system after n transitions, and we want to see how we can calculate that one. Okay, so basically we want to know what is the probability that state of the system at time n is, for example, j, if we know the probability distribution at time 0. So if we know at time 0 what is the distributions of the state of the system. We just know the probabilities associated with possible states. I don't know exactly where I am at time 0, but I know the probability distributions associated with the state of the system. And remember, these elements Q1, for example, shows that probability that the state of the system at time 0 is 1. Probability that the state of the system at time 0 is 2. Probability that the state of the system at time 0 is S. Okay, so this is what basically vector Q means for us. So knowing the probability distribution of the state of the system at time 0, what is the chance that after n transition we end up at the state j? We want to find that. So basically we can, since we don't know exactly where we are at time 0, we can condition on possible scenarios that we can be at time 0. I can write this as probability that I'm at a state j after n transition if right now at the start I'm at a state 1 multiplied by right now I'm at a state 1, or probability that after n transition I end up at a state j if I know right now I'm at a state 2 multiplied by probability that right now I'm at a state 2. And we can condition on possibility that right now I'm at a state 3, then after n transition I end up at a state j, and so forth, all the way to probability that after n transition I end up at a state j if right now I'm at a state s multiplied by probability that right now I'm at a state s. Okay, so this is just basically the total probability theorem. So I want to know what is the probability that after n transitions I end up at the state j. So I just condition it on all possible scenarios where I can be initially and I end up at the state j after n transition. So we do all these conditional probabilities and then we add them up because we don't know exactly which scenario happens. So that's what I mean. Scenario 1 happens, or scenario 2 happens, or scenario 3, all the way to scenario S. Okay, so if we can calculate this probability, then we have the answer to this question. So let's see what is the values of any one of these elements. So I have the value of this element, and what is that? That's probability of going from state 1 to j in n transition, right? So that's what this phrase means. What is this one? That's probability of going from state 2 to state j in n transitions. And how about this one? That's probability of going from state S to state J in n transitions, right? So we can calculate obviously these transition probability, these n step transition probabilities from an n step transition probability matrix. And then how about these other terms? So how we can get this one? So what is this? What is this? What is this? So those are all the terms that we already have from vector Q. So these just shows that these shows the distribution of the state of the system at time 0 if I'm at the state 1, or if I'm at the state 2, or if I'm at the state 3, or any state S. Okay, we have those values from vector Q. That's the one that is going to give us. So I can then rewrite this statement as probability of 1j after n transition multiplied by q1 plus p2j after n transition multiplied by q2 plus all the way to probability of sj after n transition multiplied by qs. Okay, so remember the values of q1 is this, value of q2 is this, and the value of qs is this. So basically this initial probability that I was looking for can be written finally as this. Okay, and so at the end I can rewrite this long equation as, okay, so if I want to calculate probability that after n transition I end up at state j, if I know if I know the probability distribution of the state of the system at time 0. I don't know exactly where I am, but I know with the chance of q1 I'm at the state 1, with the chance of q2 I'm at the state 2, all the way with the chance of qs I'm at the state s. So I can just rewrite these equations that we just calculated here, and so this is equals to sigma p ij after n transition multiplied by qi, I from 1 to s. So this summation, this sigma, is just exactly equal to this long statement that I have at the bottom. I just wrote it as a summation so that it's shorter. So that helps us to calculate the chance that after n transition we are at state j if we don't know exactly where we are right now, but I know probability distribution of the state of the system at time 0. And if I calculate those probabilities for all possible states, so I find out what is the chance that after n transitions I'm at the state 1 if I don't know where I am exactly right now, but I know vector q0, which means that is the probability distribution at time 0. What is the probability that after n transition I end up at the state 2 if I don't know where I am right now, but I know where the probability distribution at time 0, and I do this all the way to probability of xn. That after n transition we end up at the state S. Given that I don't know where I am right now, but I know the probability distribution of the state of the system, if I can calculate all of these, this will give me probability distribution of the state of the system after n transition. So this is basically what we want to calculate. Okay, now let's see how we can do the calculations for what we need. Remember one more time, we need to calculate probability that after n transitions we end up at a state j if I don't know exactly where I am right now, but I know probability distribution of the state of the system at time 0. Okay, and we just calculated together that this probability is. So let's see how we can calculate this probability. Okay, so let's write down vector q, q1, q2, all the way to qs. And now I want to multiply this vector by the n-step transition probability matrix P. So now let's assume I pick the jth column of this matrix. So what are the elements of the jth column of this matrix? They are P, probability that I go from state 1 to J in n transition, probability that I go from state 2 to J in n transitions, all the way to probability that I go from state S to J in n transitions. Okay, so this is basically how the elements of this n-step transition probability matrix P looks like, right? So now let's multiply the vector Q by the jth column of the n-step transition probability matrix P. And let's see what do we get. What we get is P1 Jn multiplied by Q1 plus P1 P2 Jn multiplied by Q2 all the way to Psjn multiplied by Qs. Okay, so or if I write it as a summation, this is just sigma P I J multiplied by Qi. I goes from 1 to S, right? So as you can see, this statement that I just wrote here equals to this statement that I need to calculate this probability. Okay, so what does that mean? That means if I multiply vector Q by the jth element of the n-step transition probability matrix, I will find out that what is the probability that I end up at the state J after n transition. So I'm going to again show it by Qj. So that's the probability that after n transition I end up at the state J. If I multiply vector Q by the first column of this n-step transition probability matrix, that gives me the probability that after n transitions I end up at state 1, no matter where I am right now. I don't know exactly where I am right now. I just know the probability distribution. So no matter where I am right now, after n transition, this is the chance that I end up at the state 1. If I multiply vector Q by the second column of this matrix, that gives me the probability that after n transition, I end up at state 2, no matter where I am right. So we can do all these calculations, and at the end we can find Qs, which is calculated by multiplying vector Q by the last column of the n-step transition probability matrix P. And again, that shows me the probability that after n transitions, I end up at the state S, given the fact that I don't know where I am exactly right now. Okay. So this is basically the probability distribution of the state of the system at time n or after n transitions. We also call it as Qn. So Q0 shows the probability distribution of the state of the system at time 0. Qn shows the probability of the state of the probability distribution of the state of the system at time n. So this calculation basically help us to go from Q0 to Qn. So let's look at an example and get a better sense on what these calculations mean. In this example, we are going to again look at the cola company that we talked about in previous videos. So in this example, let's assume we have done a marketing analysis right now, and we have found that 60% of people drink cola 1 and 40% of people drink cola 2. So what is this information? So just pay attention that these numbers 40% and 60% are not transition probabilities. If it was transition probabilities, I would tell you 60% chance that the person who drink cola 1 will drink cola 1 or cola 2 in the next purchase, and so forth. But this is not how this information is given to you. It just says 60% of people drink cola 1, 40% of people drink cola 2. So what is given here to you is probability distribution of the state of the system right now at time 0. So what I have here in the first line is Q1, and what I have here in the second line is Q2. Q1 stands for cola 1 and Q2 stands for cola 2. So what does that mean? The probability that right now I'm at time 0, I'm drinking cola 1 is 60%, and the probability that if we pick any person at time 0, that person is drinking cola 2 is 40%. So this is the probability distribution of the state of the system at time 0. the first element is 0.6 and the second element is 0.4. Okay, so the first one for cola 1, the second one for cola 2. We also know the one-step transition probability matrix for this problem. So in the question, what we want to find out is that what is the probability that 3 purchases from now, a typical person that we pick is drinking cola 1. That's what we want to find out. Just note that in this question, it doesn't tell us what is the chance that 3 purchases from now a person is drinking cola 1 if I know right now if that person is drinking cola 1 or cola 2. So I don't know exactly where is that person right now, if that person is a cola 1 drinker or a cola 2 drinker. I don't know that part. All I know is that there is 60% chance that that person is a cola 1 drinker and 40% chance that the person is cola 2 drinker. That's all I know. And then I have to find out that for a typical person, what is the chance that 3 purchases from now, that person is a cola 1 drinker. In other words, I have to calculate Q3, meaning that the probability distribution after 3 purchases or after 3 transitions. So for that, I'm going to multiply vector Q0 by 3-step transition probability matrix. So Q0 is 0.6 and 0.4. The 3-step transition probability matrix is, we obtained this 3-step transition probability matrix from the previous example. And so if we multiply vector Q0 by P3, we will have the probability distribution of the state of the system after 3 transitions, and that's going to be, so this value shows the probability that after 3 purchases a person is a cola 1 drinker, and this number shows with 36% chance a person after 3 purchases is a cola 2 drinker, given the fact that we don't know where they are right now. We don't know exactly their state right now, but we know that 64% of the population will be a cola 1 drinker and 36% of the population will be a cola 2 drinker. So this basically helps you to see what is the probability distribution of the state of the system after 3 transitions or 10 transitions or after n transitions, given the fact that we know the probability distribution of the state of the system right now.